Most people think nuclear energy belongs to the past, but in reality, nuclear power is rapidly becoming one of the most important infrastructures of the future. As the world electrifies, builds massive AI data centers, and pushes toward carbon-free energy systems, demand for stable 24/7 electricity is exploding, and that is exactly where nuclear energy becomes critical. Unlike solar and wind, nuclear power provides reliable baseload electricity at massive scale without carbon emissions. It is one of the only energy systems capable of supporting industrial economies around the clock. At the core of the nuclear renaissance are four powerful global forces converging at the same time. The first is energy security. Countries around the world are trying to reduce dependence on unstable oil and gas supply chains following years of geopolitical disruptions. The second force is the push toward net zero. Governments need carbon-free electricity systems capable of powering entire economies without sacrificing industrial productivity. The third force is grid stability. Renewable energy is growing rapidly, but solar and wind remain intermittent. Nuclear power provides the constant energy generation required to stabilize modern electrical grids. And the fourth force is AI and data center demand. Hyperscale AI infrastructure consumes enormous amounts of electricity, and nuclear energy is increasingly viewed as one of the only scalable long-term solutions. To understand how this ecosystem works, you need to break it into 5 major pillars. The first pillar is nuclear fuel and the supply chain. This includes uranium mining, enrichment, and the fabrication of high-density fuel rods used inside reactor cores. The second pillar is Small Modular Reactors, or SMRs. These next-generation reactors are designed for faster deployment, factory-based manufacturing, and integration near industrial facilities and data centers. The third pillar is operations, maintenance, and safety. Nuclear plants require advanced digital monitoring systems, precision engineering, and strict safety protocols to operate reliably over decades. The fourth pillar is waste handling and storage. Specialized systems are required to transport, contain, and securely store spent nuclear fuel under strict regulations. And the fifth pillar is fusion and next-generation innovation. Around the world, companies and governments are investing heavily in advanced reactor technologies and nuclear fusion research that could transform global energy production in the future. Behind the scenes, nuclear systems operate through highly regulated and extremely complex industrial processes. Operators continuously monitor reactor performance, cooling systems, fuel cycles, and grid integration to maintain stable energy production 24 hours a day. The nuclear value chain follows a clear structure: uranium processing, fuel fabrication, reactor operation, grid integration, and finally, long-term waste storage. Now, who is actually buying nuclear power? Big tech companies and hyperscale data center operators are increasingly signing long-term agreements for carbon-free electricity to power AI infrastructure. National utilities are replacing aging coal plants with stable nuclear baseload generation, and heavy industrial sectors like steel, chemicals, and manufacturing require constant high-temperature energy systems to decarbonize industrial production. Now let's talk about monetization. Nuclear operators generate revenue through long-term power purchase agreements that provide stable recurring cash flow. Companies also make money through uranium supply contracts, infrastructure licensing, reactor technology, and specialized engineering services. Now, let's talk about what is driving the nuclear renaissance forward. One of the biggest forces is what many now call the nuclear for AI deal. Massive AI data centers require enormous amounts of stable electricity around the clock, and large technology companies are increasingly financing the reopening, expansion, and future development of nuclear facilities to secure long-term power supply for artificial intelligence infrastructure. Another major driver is the commercialization of small modular reactors, or SMRs. The industry is now shifting from experimental prototypes toward factory-scale manufacturing, allowing reactors to be deployed faster, cheaper, and closer to industrial sites and data centers. And another important opportunity is hydrogen production. Nuclear energy can generate the constant high-temperature heat required to produce green hydrogen at industrial scale, creating potential applications across heavy transportation, shipping, and industrial manufacturing. As this trend accelerates, some of the industries most exposed include utilities, hyperscale data centers, uranium mining companies, and specialized industrial engineering firms. But despite all the momentum, nuclear energy still faces major risks. One major challenge is capital intensity. Traditional nuclear projects require enormous upfront investment and often take years to complete. Another issue is political and public perception. Safety concerns and the legacy of historical nuclear accidents still affect policy decisions around the world. There is also heavy regulatory complexity. Nuclear energy operates under some of the strictest safety and licensing frameworks in existence. And finally, long-term waste storage remains one of the biggest unresolved structural issues in the industry. At the end of the day, the nuclear renaissance is not simply about energy production. It is about building the stable, carbon-free infrastructure required to power the next generation of industrial growth, electrification, and artificial intelligence. And in a world increasingly driven by electricity demand, nuclear power may become one of the most strategic infrastructures of the 21st century. If you want to understand markets, you have to understand this system. Subscribe to NAVIXA for clear, structured market insights.